So we've spent a long time talking about limits and different properties of limits and type of limits and things like preserving limits and reflecting limits. And we want to wrap up this discussion with a bit of a challenge exercise. So there's sort of three levels to this. There's like an easy, a difficult, and a medium, I guess you could say. And so the difficult version would be to just take this theorem and prove it. So you might need to review some of the videos. I'll include some of the prerequisites with some of the definitions. That would be the difficult version. Basically just go from here and pause the video, keep it paused, and see if you can prove this whole thing, and then check the video afterwards to see if you're right. The medium difficulty version would be, let me remind you of all the definitions first. So that's what I'm going to do right away. I'm going to go through all the definitions that are needed in the statement of this theorem to be able to prove it, and then try from there. So once you have a refresher on all the different definitions that we've gone through, you can try proving it from there. It might be a little bit easier. And then the easy version would just be to follow along with me. Maybe take it a couple small steps at a time and just follow along with the video. Maybe see if you can try a couple steps, check if you're right, and then just continue to follow along that way. So you can kind of take it however you want, but let's start with the statement of the theorem. So suppose C is a complete category, and that G is a functor or a diagram, either one because they mean the same thing, from C into some other category B that both preserves limits and reflects isomorphisms, then G also reflects small limits. So there's a lot of moving parts there, sort of a lot of definitions we need to know. So that's where the refresher might come in handy. But if you want to try to prove it from here, go ahead or follow along as we go through first all the definitions that we need. So first, we suppose that C is complete. And what does complete mean? It means that every small diagram has a limit. So every small diagram D going from an index category J to a category C has a limit in C. And what is a small diagram then? Well, a small diagram is a diagram D where the objects of the index category J form a set. J is not large enough to form a proper class. A small limit is just a limit over a small diagram. So that's small limits here. And then we need to remember preserve and reflect limits. So preserving limits means that if L with the vertex L and legs Lj for each J and J form a limit over D, the diagram D, then the image of L under our functor G here, which consists of G of L and the legs G of L, is a limit over the composition of G with D. So it preserves limits, right? Even when we follow the image of this limit in C, we get a limit in B. And then reflecting limits sort of flips that definition on its head. And remember that reflecting limits has two versions, and so does preserving limits, actually. I just didn't write it here since it doesn't apply. But we can have the small and the non-small version. So let's look at the non-small version first. So reflecting limits means that anytime L is a cone over a diagram D, where the image of L under G is a limit over this composition. So here we knew that the original cone in C was a limit, but here we're saying the image of this L is a limit, then it forces L to be a limit in C, right? So here we said we know L is a limit, therefore its image is a limit. And here we're saying we know its image is a limit, and therefore it must be a limit. And not only that, but it must be that exact cone that is the limit as well. So before we move on to the small version, let's notice something. Here, the definition that we've seen and that we've repeated here is about reflecting limits. But in the statement of the theorem, we're talking about reflecting isomorphisms. So how does that make sense? Well, the only way for this to be well defined would be if isomorphisms somehow satisfied the definition of limits. And that's actually true. So that's going to be an exercise. Why do isomorphisms in a category satisfy the definition of a limit? And I'll give you a hint here. We can say that an isomorphism going from A to B in a category is isomorphic, that is, it's an isomorphism, if and only if A and I, the pair, is a limit over the category containing, or the diagram containing just the object B, the singleton B, right? So I'm not going to prove this. I'll leave this as an exercise. You can show that any isomorphism is a limit over a diagram containing only the codomain and vice versa. So now with this fact in mind, this idea of reflecting isomorphisms makes sense, right? It's not that we reflect arbitrary limits, but we reflect limits where the diagram is just a single object, right? And so what this would mean is that it's kind of like a restriction on the idea of reflecting limits. We have to find a one-legged cone, right? See how, notice this is just a one-legged cone? So we need to find a one-legged cone in C such that the image of that one-legged cone forms a limit over the composition of G with our singleton object diagram D here. And if that's the case, then we know that that limit forms an isomorphism, right? The isomorphism part of, or the morphism part of that limit is an isomorphism based on this fact. And then we know that L itself, which is also going to be an isomorphism, since it's going to be a limit over a single object, just like this one will be, then that will also be an isomorphism, and it will also be a limit, therefore. So those are the conditions on our functor G here. It preserves limits. That is, if you take a limit and apply G to it, then the result of that is also a limit, and it reflects isomorphisms. So it reflects limits anytime the limit is over a singleton diagram, which means that this L is a one-legged cone. So we have a one-legged cone where the image forms a limit, and that means that the original cone itself must also be a limit, and both of those cones would have the property that the morphism is an isomorphism, because both L and G of L are limits over diagrams containing a single object. And so we're almost done with the definitions. The last thing we have is just the small version of reflecting limits, because G reflects small limits. So what does it mean to reflect small limits? Well, we basically just fill in small here. So this just applies to small d's, small diagram d's. So if L is a cone over a small d, that is where J has objects which form a set, then the reflection property applies. So that should be more or less all the definitions you need in order to prove the theorem. As you can see, there's quite a lot to unpack. There's quite a bit of definition that we need to remember, but once we kind of do that, then this statement of this theorem is fairly straightforward. So if you're going to try the medium difficulty version of the challenge, feel free to pause the video here and see if you can use this list of definitions to prove this theorem. I would say it's still quite a challenging exercise, so at any point, if you have difficulty, just come back and check up to your progress in the video and continue on from there if you want. Or if you're going to try the easy version, then follow along with me and we'll continue on to the proof. So let's start with our assumptions here. Suppose C is a complete category and that G is a functor going from C into B, which both preserves limits and reflects isomorphisms. And we need to show that G actually reflects all small limits. So here we know that it reflects isomorphisms, and this would actually be a type of small limit, right? Because if the diagram for the limit is just a single object, then it's obviously a small diagram. So this would be a type of reflecting small limits, but we need to know that it reflects all small limits. So how do we show this? Well, we need to take a small diagram D. So let D going from J to C be small, and it needs to have a cone L, maybe vertex L and legs Lj for each j and j, such that the image of L under G, which is G of L and G of Lj for all the legs, is a limit over the composition of G with D. So that's basically the image of our small diagram D under G. So to make things easier, let's draw things out. So we have an index category J here, which maps by the diagram D into our category C. So this is D here in C. And then we have a cone L over D here, such that the image under G in the category B, so if this is our diagram, so this would be G after D now, right? Either the composition of G with D, since they're both just functors, or you can think of it as applying our functor G to the diagram D, and that's what we get here. And so it has a cone G of L over it. And not only that, but it's a limit. So this is just a cone here, but this is a limit. We know it's a limit. And we need to show exactly that this is a limit, right? Because that means that it reflects all small limits as long as our diagram is small. So we've assumed that our diagram is small here. Well, notice that since C is complete, we know that D is a small diagram, so it has a limit in C. So maybe we'll call that A. So this is a limit over D. So we can say there exists an A which consists of the vertex A and the legs AJ for every J and J, which is a limit over D, right? And we need to find that L is also a limit over D, so they need to be isomorphic, right? And so if A is a cone over D, then if we map it by G, we also have a cone over the composition here, right? Because functors always preserve cones. But not only that, G preserves limits. So G of A is actually going to be a limit over this composition, right? Not just a cone. So we have that G of A is actually also a limit over the composition of G and D. So we get that we have another limit G of A here. And what happens when we have two limits over the same diagram, right? Because we know that G of L is a limit, and we know that G of A is a limit. So when we have two limits, we know that there's a unique mediating morphism, or a unique cone morphism, maybe call it theta. So there exists a unique theta going from G of A into G of L, such that, well, it's a cone morphism, so it's the unique morphism that commutes with all of the legs of both of the limits, right? So what that means is that GLJ after theta, so that's going this way, has to be the same as G of A. G of AJ, and that's for all J and J, right? Every leg commutes by theta, and we know that theta is an isomorphism, because any two limits are isomorphic, and they're isomorphic by the cone morphism between them. So at this point, we might be tempted to say, well, that's great. We found theta. It's an isomorphism going from G of A to G of L, and G reflects isomorphism. So that means we have an isomorphism going from A to L. And so we're done, right? But that's not what reflects isomorphisms means, right? Reflects isomorphisms means we have a one-legged cone here that maps onto theta. And if that's the case, then we know that theta reflects that isomorphism back into this category. But we don't know yet whether or not there's anything that maps onto it, right? It's not that just any isomorphism gives you an automatic isomorphism in C. It's that you need to first find a one-legged cone that maps onto that morphism, that isomorphism, and then you can make the claim that it reflects it back into C. Now, of course, this also works in the other direction, right? There exists a unique X, let's just say, going this way from G of L to G of A, because they're both limits, so they're isomorphic, so it will work in either direction, so such that this case it's G of AJ after X is equal to G of LJ, and we know that X is equal to theta inverse, right? Obviously, the only isomorphism that's going to work going in this direction that's going to satisfy everything is going to be the inverse of theta. Now, looking back at C here, we maybe don't have a one-legged cone going in this direction to match theta, but we do have a morphism going back in the other direction, because A is a limit over D and L is a cone over D. So there has to be a unique mediating morphism, maybe call it U, going from L into A, right? Since A is a limit. Now U is a cone morphism, so it commutes with all of the legs of both of the cones or the cone and the limit. So we have that AJ after U is equal to LJ. It commutes with all of the legs for all of the J and J. But if that's the case, we can apply G to this whole equation, or to both sides of this equation, and we get G, and then obviously we can distribute it on this side to get GAJ after GU equals GLJ. And that also satisfies this equation, right? It can satisfy X. That's what this equation is here. So we know that this also has to be equal to G of U. But what does this mean? This is saying exactly that we have a one-legged cone, right? U can be thought of as a one-legged cone over the diagram containing only A, and it maps into an isomorphism. So that's exactly the conditions that we need to satisfy the property of reflecting isomorphisms. So we know that since it maps into an isomorphism, it is itself an isomorphism. So this equation here implies that U is an isomorphism. So all of the legs of our cone L commute with all of the legs of the limit A by an isomorphism. And that's exactly what we need to say that L Lj, which is equal to L, is a limit over D. And that is QED.